The union rule is a way of figuring out the number of elements within a union of two sets by given the number of elements in the first, the number of elements in the second, and the number of elements in the intersection of the two. So one way to think about the union rule, let's say we have, I don't know, 6 elements in here and 7 elements in here. This is A, this is B. And we know that there's 2 elements in their intersection. If I wanted to find the size of A union B, what this says, well, first off, let's see n of A. How many elements are within A? Well, let's see, there's 6 here and there's 2 here. That's all within A, so n of A is 8. N of B is, well, there's 7 here and there's 2 here. N of B is 9. Now, I said to make sure you're clear when I add numbers on these. These numbers that I'm saying here are the number of elements within each of these regions. And this 2 is specifically the number of elements within this region. This 6 is specifically the number of elements within this crescent moon. And so you can see that's why I said that n of A is the number. I would have to add these together and say that n of A is 8. So the size of the union, well, if I knew the breakdown like this, I could just say that this is 6 plus 2 plus 7. You know, that would be pretty straightforward. This would be 15. But the union rule gives us kind of a way of figuring that out if we just knew the size of A, the size of B, and the size of the intersection. Well, the size of the intersection here is 2. So this should be equal to 8 plus 9 minus 2. 8 plus 9 is 17. Subtract 2, we get 15. That checks out. So the union rule basically says, okay, if you take all of these elements, add them to all of these elements, you end up double counting the intersection. And so you just end up having to subtract that off. That's what this part is right here. You take all of the first set and add it to all of the second set, but you've double counted that intersection, so you have to subtract it off, and you end up getting something like this. Okay, so like I said, it's kind of silly if you already know the breakdowns of these. You could just say 6 plus 2 plus 7. Where it's useful is in a situation like this. We know that A has 8 elements in it, B has 12 elements in it, and we know the size of, well, it looks like we actually know the size of the union here. So let me see how I could use this. This particular formula does not have to be used in the way I initially stated it. It's a formula. It's an equation that's always true. So we could just plug stuff in. If I know the size of the union, I know that 15 is equal to 8 plus 12 minus the size of the intersection. And, well, this is something I can solve. As far as how I would solve this might be kind of a long way of going about it, but I could see somebody doing it this way. First, adding these together. Subtracting 20 from both sides, we get negative 5 equals the opposite of n of A intersect B. And thus 5 is equal to the size of A intersect B. I said that this is kind of a long way of going about it because let's think about the union rule. The way that it's stated up here, this gives us the size of the union, and we're using the size of the intersection. If we kind of just solve this in its generic form, we could actually state the union rule in a second way. We could say the size of the intersection, is equal to, let me move this down a little there, is equal to the size of the first plus the size of the second set minus the size of the union. So the union rule actually could be stated in either of these two ways, and both of them are, either is just as valid because it's just an algebraic manipulation to get from one to the other. If you start with this thing, add the size of the intersection to both sides and subtract the size of the union, you end up with this one. All right, so how that might end up working on this one is if you took 8 plus 12 minus 15, this would end up giving you the size of the intersection. 20 minus 15, which is 5. All right. Here we have the size of the union, we have the size of the first set, and we have the size of the intersection. Well, okay, that means 269. Actually, let me write the formula down first. The size of the union, and it doesn't matter that I'm changing the name of these. I used A and B up there, I'm using E and F down here, it doesn't really matter, is the size of the first plus the size of the second minus the size of the intersection. Plug in the numbers I can. 269 is equal to the size of the first, plus, well, I don't know n of f, so I'm just going to keep calling it n of f, minus the size of the intersection, which is 71. Well, using some algebra here, I know that subtracting 71 is the same thing as adding a negative 71, which allows me to move it over here, and I can do 211 minus 71. Oops, minus 71, which gives me 140. So I have 269 equals 140 plus n of f. And subtracting 140 from each side, 269 minus 140 gives me 129. So a couple of steps, and I'm able to find the size that the second set must be. And this is kind of without knowing more specific of what's going on with these individual sets. As with any formula, if you know three of the, well, this is 4 different numbers on here. If you know 3 of the 4 parts, you can use that formula to find the fourth.